Okay, g'day all, welcome to another video. So today we're going to start a brand new topic. This is going to be multi-threading in assembly, so this will probably be just a little mini-series, and it's the logical carry-on from the x64 assembly and C++ videos that I did. I'm not really happy with Imagen anymore, so I think I should make a new one, a better one with layers and selection tools. This is going to be unreal. I hope to begin working on Imagen 2 at some point. But we will get back to our BoxBlur eventually and just finish that up. It'll be from a new perspective though, which is multi-threading in assembly. Okay, so first things first, I want to sort of go through just a bunch of groundwork before we do some coding at the end, because in assembly, multi-threading is a little bit more detailed. I mean, everything's a little bit more detailed. So I just want to, I don't know, make sure that I fill in some gaps so that I don't have to go through things later. Most modern CPUs have more than one core. You probably know this already. A core is just like a little CPU sitting on the big CPU, or that's not a good way to explain it, but a CPU is really like a bunch of little cores. Yeah, it looks something like this. So we've got a multi-core CPU, might have 4 cores, like it could be a quad core, and then that's plugged into the motherboard, and from there it's connected to the system memory and peripherals and things like that. We'll go into more detail in just a second. Okay, so a core is a physical piece of hardware that's sitting on the motherboard. A thread is pretty similar, but it's a software abstraction of the same thing. So threads and cores both execute code from memory, but the operating system can actually create more threads than there are physical cores. And what it does is it divvies out the workload of, say, 100 threads to the 4 cores of a quad-core processor. Yeah, so there's sort of just a queue of different work that's got to be done in maybe 100 different system programs running in the background of Windows, and Windows is going to divvy out the workload to these 4 cores and hopefully get all of the work of 100 threads done. So the point is really that a core is a physical piece of hardware, and a thread is a software version of the same thing. So the operating system actually does what's called task switching. It puts a thread on a core for a little while. They call it a time slice, and then after a little while it saves the state of that thread and takes it off the core. It gives another thread the access to that core, so that, you know, each thread can execute a bit of its code, and eventually we'll get through lots of work, hopefully. Okay, so cores, threads, and registers. This is where things sort of take a bit of an assembly sort of turn. Each core's got its own set of registers, including the x86 general purpose registers and all the pointers and things like that, the stack pointer and that. The MMX registers, the FPU, x87, the SSE and AVX registers. Each core has its own copy of those. They've also got debugging registers and performance counters, which we've really not looked at very much, maybe except for RTDSC, the timestamp. The cores don't share their registers. Yeah, so core 0's RAX has nothing to do with core 1's RAX, and collectively the registers really form the state of the core. Yeah, so that's one of the things that the operating system saves as it switches the threads on and off the physical cores. Yeah, it saves the state of the thread's registers, so that later on, when it gives that thread another time slice on the core of the CPU, we can remember what we were doing with our thread. Okay, so yeah, I should probably just mention that there is a difference then between a core and a thread, but it's the operating system that controls when threads are switched on and off the core. So for us as programmers at this kind of high level, cores and threads are basically the same. When I write a program that splits into a couple of threads, I'm generally expecting that those threads will run on separate cores. But it is the operating system that decides that in the end. Okay, so caches. We've not talked a lot about caches, and I hope eventually to make videos on this topic too, because it's a very interesting topic. caches are a small portion of memory that resides on each core, or they're sometimes shared between the cores. In x86 CPUs, I think all of the available x86 CPUs, the caches are L1, L2, and L3, and I think only the L3 cache is shared between cores, whereas the L1 cache and the L2, each core has its own copy. I could be wrong there, and that's probably hardware dependent, depending on what CPU you buy. I believe there's still probably some CPUs out there that only have 2 levels of cache, L1 and L2. But caches are automatically used by the hardware, so we're not really going to talk about it very much here. Okay, which leads to this great big diagram. So this actually took me a lot more time than it looks. I tell you what, I don't know what's happened, but something in the last update of OpenOffice, something has caused it to just repeatedly crash. It's a real pain. It's a real pain. Apache, if you're listening, fix it, fix it, fix it. Okay, but here we go. So this is a 3-core CPU, which I don't think there are any of these. Usually you get dual core or quad core or even 8-core. But this is a 3-core, why not? And here we can see the CPU. So the CPU is this great big, I guess, lilac or lavender box just here. Yeah, and on the CPU, it's got 3 cores, core 0, core 1, core 2. Each of those cores has their own registers, and they've also got their own L1 cache. And then down here in a box, I've got L2 and L3 cache. So those are on the CPU, but the cores of the CPU share those. And like I said just before, the L2 cache might not actually be shared. It could be in these cores. Yeah, it's just up to the designers of the CPU. Intel and AMD usually. Okay, so outside of the CPU, we've got the motherboard and the rest of the system. So this will be your system memory, your PCI buses, and all of that good stuff in the in the rest of the computer, even your hard drives and all that sort of thing. Okay, so that's just a general image of a multi-core CPU. But what I want to say is that you don't have to take my word for it and my dodgy diagram drawing. What you can do, and this is really, really fascinating stuff. There's a whole art form dedicated to taking images of CPUs without their pants on, so to speak. It's called a CPU die picture, and if you just look CPU die up on Google, you can actually see incredible pictures of CPUs where you can clearly make out the different cores, the caches, registers, arithmetic units. It's fascinating stuff. They really do look like ultra complicated little cities. Just brilliant. Have a look at some CPU dies, folks. Okay, but we might just start getting into a little bit of multi-threading programming so that we can do some coding at the end. So the general strategy to multi-threading, and this is just on the most basic level, is if you've got a great big problem, like this one over here on the left, this is a huge problem for little Pac-Man. So Pac-Man here is my core, and he's got a big problem. What he would do is just execute one line at a time, blah, 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 taking maybe 2 hours or something to solve this big problem. That's fair enough. But what we might do is actually split this big problem into 2 halves. Yeah, the first half and the second half. And we might run 2 cores at the same time. So one core works on the first half. At exactly the same time, a second core or a second thread of our CPU can work on the second half. And at the end, we've solved our problem in half the time. Yeah, so it would only take 1 hour now if it took 2 hours before. That's the objective. That's very broadly speaking the objective. It is a lot more complicated than that, but that's the objective. Okay, let's just move along. So we're really getting into some syntax here. We're going to be using the CreateThread method function call, yeah, which is a Windows specific function call, and Linux does things differently. Yeah, so you've got to include windows.h. Yeah, include windows.h. We'll do all this at the end. And then this is the function that we're calling. This is the prototype to the function. So this is defined in windows.h. It's ugly, really. Yeah, it's very, very ugly. But yeah, so is a lot of Windows programming. I don't know who was in charge of the syntax to Windows programming, but they lost the plot. They really lost the plot. Anyway, this is not a critique of syntax. LP security attributes. Let's just go through the parameters one by one. Yeah, it's not real hard if you get down to it. It's not real hard. I would say, if anything, it's easier to call these Windows API functions in assembly than it is to call them in C++. Just because in assembly everything's just a number. You know, everything's just a D word. It's easy. All right, so LP security attributes. We're actually just going to leave this as null, but you can set it if you want to allow and disallow new thread handles from being inherited. The next parameter, the stack size, you can set the stack size of your newly created thread to something other than your calling thread. I think if you have 0, yeah, here it is. If you have 0, it means use the default stack size, which is whatever stack size the calling thread had. That's generally what I tend to do, but if you want some little worker thread in the background, maybe you don't want it taking up a lot of memory, so you might decrease that stack size. You know, it's up to you. Yeah, good. Stack size. LP start address. Okay, so this is the function that we want the new thread to start executing. So when you create a new thread, you've got to give it some code to start executing. You know, it's got to have some starting point. So that's what this is here. It's a function pointer, actually. Yeah, LP start address, function pointer. You used to be able to declare this as returning void, but don't do that anymore. You'll break things. Unless you want to break things. I mean, be my guest. It's all good. Breaking a few things has never hurt anybody. Now, dword when API just means std call. Yeah, that's the calling convention that we've been through in the past. And dword just means unsigned long. So you could, if you want, just ignore Microsoft's weird syntax and just use unsigned long _ std call. LP void, LP parameter. Okay, so if you want, when we create our new thread, we can optionally pass it some parameters. So we pass these with a void star, or just a void pointer, which means that this void star could actually point to anything. I mean, it could point to an array or a structure or just an integer. Yeah, so you can pass whatever parameters you want to your function. I think today we're probably not going to pass anything, but we'll have a look at passing parameters a bit later. What have we got here? dword, creation flags. Okay, the creation flags is what you want to do once the thread is created. So you can have the thread sleep if you want. So you can create the thread, but it doesn't do anything. It just waits. Or if you like, you can create the thread and have it start executing immediately. We might today, I think, have it just start executing immediately. If you do put it to sleep, then your main thread at some point has to call resume thread to wake it back up again. We'll have a look at all this stuff later. It's pretty good stuff. Thread ID. Okay, if you want for your calling thread, you can name your newly created thread using this thread ID. So you could name it a number like 0, 1, 2, 3, or 4, or you could have some code or something if you want. But yeah, thread ID. So if you care about, it's difficult to describe, but if your main thread cares about the ID of the newly created thread, then you might want to supply this. Threads do actually have an inbuilt ID as well. Yeah. Okay, so that's about it. Now we'll start coding in just a second, but I will give it a pause before I go over to Visual Studio. And all we're going to do today is just create a new thread. We're going to call the CreateThread function in x64 assembly and hopefully increment a variable. All right, I'll see you in a bit. Okay, I'm back again. I didn't go very far, so let's do some coding. Let's see if we can call the CreateThread function in assembly. So the first thing I might do is add a main. I've just got an empty project here called, sorry, I had headphones on. I've got an empty project here called creating a thread. So in my main I might do include Windows, not that. Yeah. I'll include Windows. I might include IO stream as well, and using namespace std because of the int main, and int I equals 0. Okay, so I is going to be the variable that our new thread is going to increment. What we'll do, I think, is make a function. We'll make a function in assembly, and this won't actually be the thread start function. This will just be the function that we jump to assembly with. I might call it CreateThread in ASM, maybe, and it'll take an int start I, and we'll call that function down here. So CreateThread in ASM, and I'll pass it our I as a variable. We might return 0 at the end. Okay, so once we call this function just here, we're going to jump over to assembly, and assembly is going to create a new thread. It's going to run that thread, and hopefully, with a bit of luck, that thread's going to increment this I variable from 0 to 1, and then it's going to return. So what we should do in the main thread just here is, after we've called CreateThread in ASM, we just want to wait for a while. While I equals 0. Okay, we'll just wait. While I equals 0, just spin loop. This is called a spin loop. Here, do nothing at all. This is not a very good way to do this either. We'll look at other ways later on to wait for a thread to finish, but for now, it should be pretty good. Okay, so once we've actually set I to 1, we want to print it out to sort of to prove it. So the value of I is handle. Yeah, something like that. Okay, so I hope that makes a bit of sense. If I just put a breakpoint there for later, we might switch over to x64. Here we go. Okay, good. And close. I'll just save that. And now we'll make our assembly file. So add a new item. I might call it asm.asm. Okay, so what do we need here? Well, we're going to have that, and we're going to have a bit of that, and we're going to have a bit of that. Okay, so one of the first things that we need to do at the top of our assembly file is declare that there is an external procedure called CreateThread that we're going to want to call. So we do that with extern, just like that. Yeah, extern CreateThread proc. That CreateThread function just there, that's the one in Windows. That's the one that we were going through in the slides. Yeah, so I'll just save that. Okay, so we might make the procedure that's going to be our thread's start function. So when we create our new thread, this will be the procedure that we jump to. I might call it thread start proc. It's a proc, and it's going to ret at some point. Thread start proc and p. Okay, so we're going to pass, by the time we get to this function here with our brand new thread, hopefully, we're going to have passed this pointer to I in RCX. So I might just inc, it's going to be dword pointer RCX. Yeah, something like that, then it can just return. Hopefully that all goes well. Yeah, okay, so we need to write this function now, CreateThread in ASM. So the only purpose of this function is to actually call the CreateThread function. Yeah. It's kind of a pretty stupid way to do things. I mean, we're only incrementing a variable here, but all that I wanted to show was calling this CreateThread Windows procedure from assembly. That's the real point of going about it in this convoluted way. I hope you don't mind. I hope it's useful. Anyway, push RBP, so that's save the callers RBP, mov RSP, and that's sort of like save, I guess, the RSP of our stack frame. Yeah, something like that. Okay, so the parameters that we need to use in order to call CreateThread are actually backwards. Yeah, I don't know if we've been through the we haven't been through it for a long time, but to actually push these things backwards onto the stack. So we'll start with the thread ID. Well, the thread ID can be 0. Yeah, 0 will do for our thread ID. The creation flags, we might push 0 as well. So this is the thread ID just here. This is the creation flags. And this actually means start immediately. 0 means start immediately, so our thread's going to start as soon as we call the function. Now we want to sub RSP and 28, so this is just reserving a bit of shadow space. What is it, like 4 quads of shadow space? We might move the pointer to I, which we were passed in this function in RCX. We might move that to R9. We might do that now instead of doing it at the end where the parameter would actually be pushed. We'll do it now because at the moment we've still got the value in RCX and we're just about to change that to the security attributes pointer. Mov R9 RCX. Yeah, so this is just move star I to R9. Star I is our parameter. So if you remember in the parameters to this CreateThread method, one of the things that you can do is pass a parameter as a void star, and that's what this R9 here is going to be. I did say in the slides that we weren't going to pass the parameter, but you know, how do we increment something without passing a parameter? Good. Mov RCX and 0, this is the security attributes. Yeah, we're not going to worry about that. We'll just put a null there, why not? And mov dx0, this is the stack size. And 0 actually means use the same stack size as the calling thread. Yeah, the calling thread. So the main thread's going to have a stack size already set up in your program's properties. Yeah, so that's just going to use the same stack size. We don't actually need that stack size for our newly created thread, but I mean, it doesn't matter. Okay, so the next thing that we're going to do is move into R8, the pointer, yeah, a function pointer to thread start proc. And this is gold. I mean, function pointers in assembly are so easy. Yeah, there you go. So you just literally move it, mov, and hey presto, R8 is a function pointer. Yeah, so if you're not familiar with the calling convention that we're using here, maybe just have a look at the other two. A long time ago we went through the C calling convention, but yeah, usually you would pass parameters 1, 2, 3, and 4 in RCX, RDX, R8, and R9. But because, you know, I was just about to change RCX to 0, I decided to put my R9 first. Anyway, now that we've done all that, we can call, well, you've got to spell it right, CreateThread, and that's going to be a big drum roll there. And then we can restore the caller's RSP. Oh, sorry, not restore the caller's RSP, that's deallocate all of these parameters from the stack. And we can pop our BP. Yeah, that's restore the caller's RBP. And ret. Okay, so it's a pretty long-winded sort of ordeal, but hopefully what we're going to have here is a second thread. And, you know, we could put any code in here that we like, so this is pretty powerful stuff. I'm going to tentatively push F5 and cross your fingers for me. Let's see what happens. I can't have typed all that stuff without a typo. One unresolved external. Create thread in ASM. Okay. Oh, you're a moron. Okay, so what I've done is I haven't included the build customization. So what we'll do is just add that now. So, masm. Okay. And because we added that asm.asm before the build customization, I will have to delete that and actually add it again so that the build customization knows that it's meant to handle that asm.asm. Sorry about that. Alright, well it wasn't a typo, it was pretty silly though. Let's see how we go now. I'll hit F5 again. Oh, would you look at that? There you go, the value of I is 1. Okay, but what's cool about that 1 there is that it was another thread, other than the main thread that actually did that. Yeah, so if we have a bit of a step through, if I put a breakpoint here on this I just here, and then I put a breakpoint up here in thread start proc, we should be able to get somewhere up here in Visual Studio a readout of the IDs of these threads, the automatic IDs. There you go. So the thread that's running main just here is 4260. And there you go. So the automatic ID of the second thread that we created is 6684. Yeah. So notice that that's a different ID to the thread ID that you can name down here as a parameter. Whew. Okay. Well, that was pretty fiddly stuff. It doesn't change though. All of this is pretty much the same. So. Yeah, hopefully it wasn't too bad. Anyway, just, thanks for watching and stay excellent, all of you. See ya.